Dear delegates, to save you and the others, I decided not to come to ICCE in person today, but to avoid a no-show, I recorded my presentation, so if you like, you can follow. So the stability of buried scour protection in shallow coastal waters will be topic of the given presentation. My co-authors are Alexander Schendel and Thorsten Schlurmann from Leibniz University Hannover, and Henry Forgen, Dirk-Jan Peters and Erik Sigtemann from Royal Haskoning DHV. I will talk about the motivation and the objectives of the study presented. I will give brief details about the hydraulic model tests for the setup, the instrumentation and the scour protection installed, and will then focus on the results. Here I will present three main topics. First, the scour evolution and the processes observed, the scour protection stability, and the sand washout from the scour protection. Regarding the motivation. So the Dutch energy company Eneco received the concession to construct a wind farm at the Maasvlakte 2 at the port of Rotterdam. Here 12 turbines will be constructed on the beach close to the waterline. The beach is highly erosive and is maintained by regular nourishments. Design and constructing wind turbines in this dynamic environment is a really challenging issue as you can estimate. So the objectives of the presented study is a verification of the scour protection design in a varying shallow water depth under wave and current load. We want to consider the main driving mechanism of the scour evolution, and we also want to quantify the washout depths in a buried scour protection. The hydraulic model test conducted. The test took place in the wave current basin at the Leibniz University of Hannover. Here you can see an image from the wave setup, the wave maker on the right hand side, and here you see the idealized cross-section that was installed here in the basin. We have a 1 in 10 transition slope and a horizontal submerged foreshore, then a 1 in 30 sandy slope where the pile is installed, and then a horizontal part as well. This is the top view of the model, and here you can see we have usually a fixed bottom profile, and the yellow part highlighted is a mobile sandbed for 4 by 4 meters. Current is introduced into the model via a 5 meter width channel from the side, and the wave propagate perpendicular to this from the wave maker. Instrumentation. Just briefly, we have wave conditions that were measured offshore and around the structure. We have the flow field with ADVs and propellers close to the pile. The scour processes near the pile were recorded by 4 cameras, and the global scour evolution was measured by a bottom profile in 2D and a laser scanner in 3D. And then there was lots of photo and video documentation. So regarding the scour protection, on the right hand side you can see a video how the filter layer is installed in red, and on top the armor layer of the scour protection. The rock scaling is based on a mobility parameter, and we used idealized grading regarding the Rosen-Ramler distribution. And the focus of this study is the damage due to shear failure. And so the washout that we observed that might be influenced by scale effect, as the ratio from armor to sand is not represented correctly, because if we would scale the sand in a scale of 1 to 40, then we would have cohesive influences. We tested 2 different configurations of the beach. One is the normal condition for 2 different return periods given here with different water levels. You can already see we have a larger pile diameter than the water level, and then we have an eroded beach configuration where you can see that only the top layer of the sand is in a lower level right now, but the armor layer itself and also the water levels tested are on the same level. This is an impression of the calibration of the currents, which has had target values of 1.75 to 2.5 meters second, and additionally the wave calibration that has been conducted before the test with the given wave characteristics that we have here. So both conditions have been calibrated individually and superimposed afterwards. This is an impression of the wave and current test. So the current is coming from left to right. You see the pile. Waves are propagating towards the structure. And you can see here our 2D bottom profiler, which enables us to estimate the evolution of the bed profile during the testing. Now I come to the results. I start with the Scour evolution and processes. So the current-induced flow was the dominating factor of the scouring of the sand layer. On the top right, you see an impression after a test with currents that has been conducted for 8 hours. And in wave-only conditions, so the scour depth was much smaller, as you can see. The hydraulic load was not sufficient to uncover the embedded scour protection, as you can see in the image, but this was somehow estimated as the KC number is only around 2. And in wave current conditions, the further progression and expansion of the scour hole was obstructed by this buried scour protection layer that we can see here. I have to mention for the current load only, during the observation, the armor layer was always stable, and we could not observe any movement of the armor rock stones. Under wave and current, as you can see on the bottom, we had a slightly rocking of this top layer of the scour protection. This is one impression of the evolution of the scour process over time. So starting from the beginning with a horizontal bed in the dark orange line on top, and you see with further testing time the scour hole evolves, and the maximum depth is limited by the installed scour protection, as you can see here. And at the end of the test, you can see we have run the test for a very long time in the beginning. So the overall shape of the scour hole did not change anymore, but you can see that the bed level itself is changed during this really long time testing that we had here. Timing given here is in prototype scale. The scour protection stability, to estimate it, we first have to define our damage. On the right-hand side, you can see an image that was derived from the 3D laser scanning of the scour protection, where we estimated the difference of the bed elevation from a scan before the test and a scan after the test. And in accordance with failure criterion by Boone et al., where the scour protection has failed when the filter layer is exposed over an area equal to 4 times the diameter of one of the armor stones. We've chosen then an approach where the damage number is defined as an eroded volume over an area equal to such an area which represents 4 times the footprint of one of these armor stones. And each of these areas is represented by one of these sub-areas that you can see on the right-hand side. By applying the formula on the top left that you can see, we can estimate damage numbers for each of these subsections. And damage number of 1 means that the armor layer is eroded by a thickness of 1 stone diameter. And the failure of the scour protection in this specific case is if the damage number is larger than 4, as our armor layer had the thickness of 4 stones. This is an impression of the maximum design load that was applied, so maximum current velocity and maximum wave loading. And what you can see, rocking is allowed. You can see on the top right, on the bottom right, some minor movements of the scour protection. It is cost efficient due to smaller stone sizes required that you allow such tiny rocking, but you have no rock displacement is allowed for these tests. This is an impression how the full scour protection looked after the testing. You see the area of maximum erosion is highlighted here. And we can also find this in the differences of the laser scanner here. And from this, we obtained the damage number for this specific test. And you can see with the S-max of 1.2 that we have about 1.2 times the scour protection armor layer stone diameter that was eroded at this position. If we bring this to a graph now, you have on the right-hand side the damage number, which is given over the flow velocity for different loading configurations that are given in the legend. And on the left-hand side we have the normal beach configuration, and on the right-hand side we have the eroded beach configuration. So what we can see is that the damage increases with increasing flow velocity. The current-induced damage decreases with an increasing water depth as well. An eroded beach leads to larger damage numbers for the same hydraulic load that we have. And the wave current load represents a decisive load case that we have, and a comparable damage trend was found for higher water levels as well. Additionally, we tested a scour protection with a lower diameter, which showed similar stability results. So this might be an indicator for an improvement to just save some money. And what we also found that the load history has a strong influence on the damage number as well. So we received lower damage number when we started with a fresh bed and the maximum design load, which indicates that if you have a fresh nourished beach and then receive your highest wave load, you will have a lower damage number than if you have a beach that is already eroded over a certain time, and then you have a strong storm coming there. Finally, I will talk about the washout from the filter layer. The same graph as you had before, but now we have the relative washout depth, which is the washout depth over the thickness of the armor layer, over the flow velocity. And what we can see is that the washout depth increases with increasing hydraulic load that we have here. The hydraulic load is higher at the eroded profile due to higher waves at the pile. So we remember that we also had higher damage numbers at the eroded profile. And when we look to the waves, we can see that for the eroded profile, we have comparable higher waves at the pile for the almost same offshore wave conditions, and this is due to the fact that we have less energy dissipation if we have larger water depths close to the pile, and even more wave energy can travel towards the pile. And what we can additionally see is that due to the disturbed Horseshoe vortex, the washout depth is reduced for a combined loading. That is what you can see here. The light circles is for current only, and the dark red circles is for an additional wave loading. The current-induced washout depth is also higher for lower water depths. This was somehow surprising to us, as it was not expected, but we could clearly find this in our results. And then we have to mention that there might be a scatter due to the sediment installation, which might be a model effect. So it was always the same person installing the sand, and it was always the same procedure as we did, but we already noticed that it is something where you really have to take care, and where we might see some minor scatter here. Here now two videos from different return periods, and where you can see the influence of the washout phenomenon in the filter layer. And as you can see on the right hand side, for the larger hydraulic loads, you see that we have much deeper washout depths. The armor layer is completely washed out, and the washout process stops at the filter layer. Concluding what we have seen. So regarding the scour protection, the current-induced flow was the dominant factor for the scouring of the sand layer. And the wave current load represents a decisive load case in this study. The design scour protection system was stable, and the washout depth is deeper at the eroded beach profile due to higher wave energy at the pile. And due to the disturbed Horseshoe vortex, the washout depth is reduced for combined loading. So thank you for your attention. I would like to highlight the presentation from Anne de Beer on Friday, tomorrow. If you are interested in this project, she will talk about the whole project. And yeah, what are your questions? Maybe one of my colleagues is in the room to answer the questions. Thank you for attending.